All right, we're going to go ahead and get started here. So today's discussion, or topic rather, is a one-on-one in time series analytics with Apache Arrow, Pandas, and Parquet. Obviously, you guys can ask questions on the Discord channel. You're also welcome to reach out to me via LinkedIn. That's what that QR code is. And other than that, I am a developer advocate at Influx Data. So a developer advocate is basically a person who just advocates for the company. We're going to briefly talk about Influx, which is a time series database. And then we're going to go into some of these other open source toolings. So the first thing we're going to talk about is why a time series database is important. Some tools to know. What is Apache Parquet and Apache Arrow? Apache Arrow examples. Leveraging Pandas for analytics. And examples of autocorrelation, anomaly detection, and forecasting. The forecasting one will be more about a take-home assignment. We're not going to go too deep into that one. And then some final resources, of which there will be many. So this is going to have some live coding examples, and then a bunch of Jupyter notebooks, basically, to take back with you. So I know this is a little awkward because we're in a theater, but if you want to raise your hand if you have worked with time series data before. All right, I see quite a few hands. How many of you have worked with the time series database? Not so many. A few less hands. That's totally normal. So why is a time series database is important? So we consider time series data three things. The big one is metrics. So that's what pretty much everyone is pretty familiar with. I normally define this as something like a Fitbit. For somebody who's not super familiar with IoT, a Fitbit is an IoT device that you're basically wearing. It regularly collects intervals, and although we don't see it on like the application, like the Fitbit app, I can assure you it's collecting metrics pretty like every second probably, maybe every minute. But basically, it is constantly collecting them. When it displays it to you, it aggregates them down, as we call it. It says something like, in the past hour, this was your heart rate minutes, not your heart rate seconds. It's probably getting it by the second, but it's just aggregating it to be more visually appealing for us. Also because if you get it down to the second and try to store that amount of data, it ends up costing quite a bit of money. The next one is events. So events tend to be state changes that are irregularly generated. So that can be things like you click on a button on a website to go shopping. No one's clicking on the button every freaking second, we hope. So basically, they're clicking on it when they click on it, and that is an irregular event. A trace is kind of like a bigger version of that. Traces tend to be events that are irregular, but it tends to be a full trace stack. So you press that button for the shopping cart, and it goes ahead and it calls for Stripe, it calls for your backend, it calls for Google Wallet, it calls for all these things, basically, when you click this one button. And you can use traces to see where things tend to slow down or crash, for example. Like you can see that the Google Wallet 400 versus everything else that came back with 200. So that tends to be what we call traces, which are basically just time series data with a lot of metadata attached to it. So I bet a lot of you guys who have worked with time series data tend to store it in a relational. That's not uncommon, mainly in the fact that a lot of people just use relational DBs for everything, for good or for bad. But normally relational are a little bit better at records that you don't tend to manipulate a bunch or, for example, delete a bunch. Time series data tends to be data where you do aggregate it. So you delete your old data that's like by the second. So for example, let's say you're a factory. You build paper towels. For the day, for your single work day, you are monitoring those machines by the second. You want to make sure the pressure's right, the temperature's right. You do not want your paper towel machines to, start printing bad words on your paper towels or blowing up or anything. So you monitor them by the second, or even by the milli or nanosecond throughout the day. But then the day ends. The paper towels were created, everything's great, and now you kind of just want to aggregate this down. You want averages for maybe 5 minutes or even for the hour, and you'll use that historical data for analysis. You'll use it for anomaly detection and autoregression, all that good stuff, but you'll tend to delete that millisecond data because you don't want to store it because it's going to cost a bunch of money, and you just don't need it. So that's where a database like a time series database, or in general, a NoSQL database comes into play. So for example, MongoDB is also very good at this because it's a document database. So it's great for this high throughput dropping of data. Same with Elastic, which is basically actually a search time series database. It obviously does a little bit more than just time series, but it definitely focuses on the analytics of searching, which can be something like, I can assure you, in December, people look up Santa more than they probably do in August. It's just going to be a thing that at that time they're going to look for. And in that same way, you can use it to obviously extrapolate things like shopping patterns for Amazon. I can assure you they stock more Santa supplies in December than they do in their warehouses in June. They just know. So this is a typical architecture and deployment. And although it says InfluxDB in the center, this is in general for any kind of time series database or NoSQL database that you're tending to use for time series, and honestly, even for SQL databases that you're throwing time series into. You tend to have your data sources, which we've already talked about. You have your data collection, which we in particular have things like client libraries, which are language specific, and Telegraph, which I highly suggest people check out. It is an open source ingestion agent, and it works with tons of different databases and about 400 different plugins. Then we have data storage and transformation, which is pretty straightforward. It's basically just the data storage, things like compression, cold storage, and then for us personally, we actually use the SQL language to allow you to query out with SQL, which is very powerful because it allows you to integrate with lots of visualization and analysis tools, things like Tableau, Grafana, Power BI. Most of these tools expect you to use some type of SQL query language, some more than others, but basically this allows a lot more interoperability. So, some tools to know. So I already talked about this one, which is Telegraph, and like I said, this one is extremely great for open source agent for collecting metrics. It's not so much for collecting traces and events, but it is ideal for metrics. It's driven by our community of about 600 plus contributors, and it's simple to configure. And here are just a few of the categories of Telegraph plugins. I'm going to leave this up for a second. So as you can see, we have things all over the spectrum. We have plenty of what you might call professional integrations. And although they're not on here, we also have some more fun. Oh, there it is. Minecraft is not what I would consider a professional integration, but it can still be fun and definitely is still very much used. But yeah, so we've obviously got things like IoT, logging, databases, who would have thought, and just in general, like I said, there's about 400 of these. And quite a few of them are supported by developers at the companies and products that you can see here. Like NVIDIA's is supported by NVIDIA devs. So although we're the caretakers of Telegraph, it's supported by tons of people. The next thing to be aware of is SQL aggregate functions. So we use a very specific version of SQL. It comes out of Apache Data Fusion. And because of that, we have access to these SQL aggregate functions. Depending on your database and just in general what data tools you're using, some of them will come with these kind of functions, some of them will not. I tend to use quite a lot of the general ones because they are exactly what you would expect to use when dealing with like IoT data. Things like mean, median, min. We also have a few, we have a much larger SQL documentation that goes over other not aggregate functions, but just in general useful functions. But these ones are specific for analytics workloads. One thing we are going to talk about later, and it's going to be used in the example, is the ADDTK, otherwise known as the Anomaly Detection Toolkit. It's an open source Python package for rule-based anomaly detection in specifically time series data. It is more geared towards industrial IoT use cases, but it can be used for, obviously, non-industrial IoT as well. It comes with all of these different anomaly. We're going to be using the autoregression AD later, but their docs are very, very good, and they give examples for all of these. Another one is TensorFlow, which we're not going to go into, and I'm just Actually, if you want a photo for this one, this is when you would grab it, because this resource won't come back. But this is for like machine learning and artificial intelligence. Data scientists tend to use TensorFlow to build and train models using either Python or JavaScript, and we have some resources for using it with Influx as well. Profit is what we tend to use for forecasting, and that's also what the forecasting examples will have. It fits the forecasting problem with what we call a curve-fitting exercise, or creating a mathematical model. It works very similar to Holt-Winters or triple exponential smoothing, but it basically is just going to combine things like seasonality, trends, and holidays. It helps you determine when to have a bunch of Santas in your Amazon warehouse. Even though it might seem obvious to you, it's obviously December, but actually it might be November 15th is the day that people order everything. You never know. That's what this can help you figure out and forecast. So, what is Apache Parquet and Apache Arrow? So, Apache Arrow is basically a way of taking the data out of something like Apache Parquet or a database engine that's taking advantage of Parquet files, and it allows you to send them onward to other data tools. I have another visualization that'll go over this even better. And Apache Arrow Flight SQL is very specific in the fact that it allows you to use SQL querying to get that data out and to send it into other data tooling. Parquet is just a file format. It's very good at storing column-based data, and it's very good for things like compression and indexing. So basically, it's a column-oriented data file designed for efficient data storage and retrieval. It is not a runtime in-memory format, and it cannot be directly operated on, but must be decoded in large chunks. The big benefits here are that it's going to minimize disk usage while storing gigabytes of data. And as I mentioned earlier, if you're dealing with IoT data, or just time series in general, you're going to be dealing with a lot. It's also really good for retrieval and deserialization of large amounts of that column or data. So for example, this is the size of data stored in a CSV file versus data stored in an Apache Parquet format. You can see the size on Amazon S3, the query runtime, the data scanned, and the cost to do that. So as you can see, it's quite a bit faster, and it stores quite a bit cheaper as well. This is being pulled from Influx because we take advantage of Parquet, so we can see this is how it looks within our own database engine. So we can see things like the file count and the size and how much smaller they become in Parquet. TSM just means time series metrics database. Basically, it's our old version. And we're proving here the fact that Parquet is obviously much faster and much better at storage for our new engine. It's not per se particularly new, it's about a year and a half old, but compared to our old engine, you can see all the cost savings. Apache Arrow is more a framework for dividing that in-memory columnar data that every processing engine can use. It's language agnostic standard, it's efficient for running large analytical workloads, and it supports a range of programming languages, including C++, Java, Python, and R, and I think actually a few others. But basically, all of our client libraries are built on top of Apache Arrow. That's what we're taking advantage of. So it obviously is going to make that data processing faster and more efficient because it stores data in a way that computers can read and work with quickly, especially when dealing with very big data sets. In particular, this columnar layout enables vectorization using the latest single instruction multiple data operations included in modern processors, which is, in my opinion, a lot of fancy words for saying that it's searching much more efficiently because of the way that it's basically stored and indexed within the Arrow memory buffer. Finally, as I kind of already mentioned, while Apache Arrow Flight and also Flight SQL, as it's called, is basically Arrow Flight allows that high-volume transfer of columnar data. It's still good for, obviously, the distributed computing and analytics workloads, and Arrow Flight SQL is basically just the SQL flavor of that. So basically what this means is that there's many database engines who are starting to take advantage of Apache Arrow, not just us. But they sometimes have their own querying language, kind of like Mongo has, I actually don't remember the name of the languages, but I know it's not SQL. And so a lot of non-SQL languages can still take advantage of Arrow Flight. They just kind of have to, obviously it's an open source project, so they have to add everything in to allow it, but SQL is just specific to the SQL query language. And I do think it accepts a few different versions of SQL, because SQL also comes in multiple different flavors. And yes, it's good for query execution, and it returns that Columnar format. This is just basically explaining what I just did, but basically it's just that the fact that, like I said before, Flight is query language agnostic. So for example, we use it for our own query language called InfluxQL, and it returns Arrow results, versus the Flight SQL, which is SQL specific. It's designed for ORMs and UI builders, and is implementation agnostic, but obviously not query language agnostic. Which one should you use? Well, honestly, it's probably just going to depend on the engine you end up using and what their language is, but we offer both because of the fact that we have two languages. So the big thing here is that there's no serialization or deserialization cost. Since Arrow data is sent directly, there's no need to serialize or deserialize the data, and no need to make extra copies of the data, which wasn't always the case. So it used to be that if you wanted to get your data out of Cassandra's into Pandas, Apache Spark, or even something like Apache Parquet to Apache Spark, you would have to copy and convert your data, which was very much not cost efficient. It's just not efficient in general. And it might seem a little silly, why would people use all these different tools? But I can assure you, quite a lot of people are using all these different tools. You use something like Influx for your time series data, maybe you're storing something different in Cassandra, and then you want to take advantage of things like Pandas and Apache Spark and all this other stuff. So now you have this one system, Apache Arrow, that allows you to connect all of the above and more than this as well. These are just some of the logos that I felt were easiest to add onto this. The ones at the bottom in particular tend to be like Influx database engines, outside of Parquet, obviously, which is a file format. But like DuckDB and ClickHouse also are pretty much built very similar to we are. And that allows interoperability between all of us. And obviously, all of the big tool sets that you can see up at the top, like pandas and polars. So basically, that's how this all kind of fits in. And again, although this has Influx at the bottom, this tends to be how things like ClickHouse and DuckDB also operate. You've got Apache Arrow, Parquet, and Data Fusion to power up the engine and basically give a lot of open source tooling that you could take advantage of. Then you have Apache Arrow with Flight SQL. And with that, you can connect to all these other technologies, some of which I've already mentioned. And it can power things like client libraries. And there is a bit of a, what's the word here, in gaming when you find like an Easter egg in here. To understand some of these performance differences, we're doing a reading of a CSV file with about 11 million records, where we compare the Pandas CSV reader, which is the default engine, with PyArrows. PyArrows does it about 15 times faster with arrows in memory columnar format, and quite a bit smaller. So obviously there's quite a lot of savings by taking advantage of this. I suppose you could say one of the few downsides of Arrow is the fact that you have to work with a database or tooling or engine, that already has it integrated. The good news is that a lot of people are starting to integrate this because it is so much faster and makes life so much easier and, to a certain extent, cheaper. So before Arrow, the conversion from something like Spark data frames to Pandas, for example, was not a very fun process. We would say it was inefficient, since it had to do both serialization and deserialization. But now, with this, PySpark achieved two advantages. There's no need to serialize or deserialize the rows, and when Python receives the Arrow data, PyArrow will create a data frame from the entire chunk of data at once, instead of doing it for individual values. So now we'll go ahead and get into an Apache Arrow example. So this is basically how you create an arrow table. It's pretty straightforward. So as you can see, we're calling it as PA from PyArrow. We're creating an array here. It's got some animals. It's got the count of animals, and it's got the year as well, of how many of these animals existed in that year. And from there, we can create a table from all of these arrays. And on the right-hand side, you can see what this looks like. You can see it's got, at the table, it also describes what these are: the string, a count with an integer of 8, and a year of an integer of 16. And then it defines these arrays, basically. What I'm pointing out here is just how simple it is. No need to go and think too much about it. So then we can use something like the Flight SQL client, which, as I said before, is specific to SQL. So with this one, we're using it with Influx, and we're querying the client, and we want to select all from the IOX machine data where the time is greater than now of an interval of 1 day. Basically, we're asking for all of the data from the past day. That's basically what the query is saying. And then we create a reader to consume that result, because we expect it to be, it's going to stream quite a bit of data, and depending on how much data you've got for the day, so you definitely want to create a reader for that. And then you want to read all that data into that Apache Arrow table, so you just say basically read all. And on the side here, you can again see that table. It's got a lot more information up at the top this time around because we have a few more values, obviously, within the table. But you can see things that it defines as strings, as doubles, as a timestamps of not null. It's mostly just strings, doubles, and timestamps for this one. And then you can see the actual information below. Obviously, when we did this for real, it was a much bigger table, but this is just a small snippet example that we can fit in a slide deck. So for example, this is what the resulting data frame looks like. So we include the top 20 values with the head function just to make sure that it returns multiple time points for each sensor. So basically here we have our humidity, our sensor ID, our temperature, and our time value. So Arrow also comes with a few utility functions, which are very handy. For example, converting it to a pandas data frame. That's very helpful if you want to work with pandas, which I tend to do quite a bit. And this one, highlighted in purple, is exactly the one that we just called for. So basically, we're converting the tables to pandas, we're sorting the values by the time, so the time is the top, and we have the head of 20. So I'm going to go back really quick just to compare. But basically, that query results in this table, which is very readable. And you can see the data is a bit old, obviously, from 2023, but the time is the most recent. The other thing you can do is you can actually load a table directly from a Parquet file. So this is kind of like a cheat code that some people are using when they don't want to use an engine that uses Apache Arrow. They can just literally load up Parquet files from something like S3 or a server, wherever you wanted to grab them, basically, and store them. The other thing you can do is you can save that table to a Parquet file. If you want to be that kind of person, you want to query it out, you want to save it to a table, and then you want to save it to a Parquet file and share that with your coworker, or just in general put up in S3, maybe it's a backup storage, you can do that. The other thing it allows you to do is things like aggregation. Very similar to what I talked about before with the SQL aggregation, but this is built into Apache Arrow. So with this, you can do things like aggregate the vibration mean, max, and min, and then still convert it all to pandas. I don't have an example of what that looks like, but you can just imagine. It's very simple. So the other thing that I also want to mention is downsampling with pandas. So this is something that a lot of people like to do with time series data. I've already kind of talked about it when you want to downsample or down aggregate, as we otherwise call it, which is basically just to get the data down to the 10-minute intervals. So we're going to use, for example, the group by function to group our data frame by sensor ID tag columns, which basically means for each sensor ID, because we might have multiple machines running. Then we use the resample and mean functions to downsample and apply a mean over all of the intervals, respectively. And then we go ahead and we create a copy of that downsampled data. So for example, we could write it back to something like Influx or another engine, or just even a straight-up Parquet file. But basically, we take that original table result, we go ahead and do the downsampling on it, and now we end up with a table that looks a little bit more like this. As you can see, the sensor ID now on the left is basically saying, like, this is sensor 100 versus sensor 203, and this is the last 10-minute intervals chunked out for the CO, the humidity, and the temperature. So obviously, this was all done in like 5 lines of code, and very simple, very easy to get going and doing. And yeah, you can take advantage of Apache Arrow's aggregation or pandas as well. And this is just a pretty quick example of how you would send that data back up And again, you don't have to use something like Influx in particular. You can send it onward to other data tooling sets. But in general, this is how most people tend to interact with Apache Arrow, is something like client write API. You're defining, for example, a bucket or a database name. And then you just want to write the data frame measurement name, mean downsampled. And you also want to set something like a timestamp column. And when we talk about tag columns, for us at least, that's something that's like a secondary primary index. So we always index on time when you do your queries and searching, but sensor ID can be your second biggest search. Like you want to always query in the past 5 minutes what was happening on sensor 100 versus sensor 203. If that's something that like would commonly be queried, that's what we would call a tag. And this is a Plotly dashboard of the example of those vibrations means, max, and minimums, as well as the machine IDs plotted out that we just saw before. So obviously you can see the vibration levels. I mean, honestly, it's just a graph. I see these so often, it's kind of funny when I have to see them on the slide deck. I'm never that impressed, per se. But it is really simple to do, and it looks really great. And it's just very easy to feed in. Obviously, now we're into Plotly. We're using Pandas. We've gone over a lot of different tools here, but it's really nice that they just all integrate together so well, that it's pretty much seamless to go between them. And this is Plotly with an ADDTK dashboard, which, if you remember correctly, was the anomaly detection toolkit. So what this is doing is it's adding all those little red dots that you see. And it's saying that these are anomalies within the vibration levels of the machines. And it's using all this data that we fed it, which isn't too much, to be fair, but it's determining what would be historically normal for this, basically. And you can kind of see visually that this second spike up is clearly what's considered the norm, because it's the one without any red dots, versus this first one has red dots at the beginning, at the end, and also down here at this bottom piece right here. That's basically saying that it expected to run longer. Like it expected the vibrations to keep going. It expected a very specific time, basically. And it's just doing that all over the entire data set, which is quite, obviously for us, it's very visually easy to see. But it's not so visually easy to see, like, if the dots weren't there. I mean, you could kind of guess on something like, hey, this one didn't seem to run quite so long as these other ones. But outside of that, this is obviously a much more efficient, what's the word here? Less human errorable version of doing that. So this is also an example architecture, and this is where some of the code lives for this example. So in this one, we're using a machine simulator running in like a Docker container where we have an MQTT broker sending data in through Telegraph. Then we use our Python script to do things like aggregation, downsampling, just in general, and also plotting, obviously. Just in general, all the stuff we just went over. And then we're also using Grafana as well in the full project. I didn't show it here, but we also have a Grafana dashboard to go along with this, something that you could obviously share. The whole point of this is to basically be kind of like a real example that our customers tend to do. And their data scientists tend to work in Python, but then some of their other people want a Grafana dashboard to reference and that they can share with a team. So that's the other thing, too, to keep in mind, is this really helps with the ability to share this data across multiple people within the company and multiple groups as well. Like I said, your data scientists might be working out of like Python script files and Pandas and Plotly, but maybe your engineers on the floor of like this factory are using Grafana dashboard instead. It's just visually on like a big TV screen or something, and it shows all the health metrics of these machines. And then 1 week down the line, this data is sent onward to somebody like halfway around the world who's comparing all of this data across multiple factories, across multiple countries, and they're using that to determine what, when they're going to call the guy in, Todd, to come fix the machine in Columbus versus when Todd needs to go to the machine in Berlin and fix it, because they have all this data to determine when the machines need to be serviced or when they're not working at optimal efficiency. Which this is a real thing. This is 100% how people do this. So Apache Arrow and Apache Spark. So this is an example of the conversion speed between, so when you want to create a Spark session, basically. One sec. And obviously, you can see the execution time between these. One of them is significantly smaller because it's taking advantage of Pi Arrow basically to convert this data frame into pandas. And the reason it's so much faster is because it's taking advantage of Pi Arrow and in general, Apache Arrow in general, versus when it's not. So there's still a little bit of work to be done here. For example, a direct integration via Flight SQL and a direct Pi Arrow table conversion. So that's what Apache Spark was telling me the last time I talked with them, is that those are two of the things that they're currently working on improving in this process. So leveraging pandas for analytics. So we already kind of started talking about pandas, but let's go ahead and dive a little deeper. Now, one thing to note is some of you guys already probably are relatively familiar with pandas. You understand how it works. So this is going to be probably a little bit of a rerun for you. And the big thing that we're going to be talking about during this is pandas joining data frames. And the reason we're talking about it is because that's a very common use case that people talk about, is they've got multiple different data sets and multiple different data toolings, databases, whatever you want to call it, maybe a data lake or something. And basically, they need to be able to join them together. And quite a few people actually get a little tripped up on how this works and what is, appropriate when you're joining data frames in particular. So we have two data frames here that have some things in common, some things not in common, and that's on purpose, so that way then as we begin to join them, we can kind of see the differences. So if you just join them with no how parameter, it defaults, as we say, to the left, which basically means it defaults to the first data frame, because the left is the first one, the right is the one on the bottom. It's just the way it's displayed in the terminal. It's a little weird, but just remember, left is the top one. So with this, it's basically taking all of the data between both of them and combining them and calling them courses left and courses right. But the only thing to note here is it's also infilling those non-values for everything in the courses right that doesn't match to the courses left. And basically, if you flip that, and you say join with a right how parameter. So if you'll notice here, right here, you'll see it says like r suffix underscore right. But then we go ahead and add that comma, and we put how. We want to do it on the right side. So now it's going to infill those non-values for everything on courses left that doesn't match courses right. So obviously, courses left doesn't have Java, so it nons out those values. And then it's also deleting, where is it deleting? It's deleting everything like PySpark, for example, because that also doesn't match the courses right. So it's not being added here. So you end up with 4 table rows, basically, and some with a bunch of non-values. If you were to do what we call an outer join, that basically means everything gets included. This is probably one of the more, honestly, common ways that people join stuff up, just because you don't want to lose any data. So now you've got this, a bunch of non-values everywhere, basically, because you're combining it all together. It still is going to call it courses left and courses right, because it knows, obviously, that they're named the same. The row name is named the same. So you've got to distinct them somehow, basically. And then the opposite of that is an inner join, where basically it deletes anything that doesn't match up on the courses left and courses right. So now we remove things like PySpark and Java and Go and Pandas, because the only ones that match are Spark and Python. So we end up with no non-values on the bright side, but we also end up with a bunch of stuff dropped. This is probably, honestly, the way that also a lot of people tend to join things, because they want to get rid of everything that doesn't match exactly, especially when they're dealing with something like SQL data and time series data, where the only thing matching is like IDs, like a sensor ID. The sensor ID has information within a SQL DB, and they don't want a bunch of non-values. They just want to inner join them. When you join on the column, it basically is going to no longer do that left and right courses anymore. Now it's basically doing the inner join, but it's just going to have courses. So let me go ahead and go back here. So as you can see, also, we've removed the R1 and the R3. So we're removing those indexes, and we just have our courses. This is basically doing just a straight join, very similar. The only difference here is that we also get to keep our indexes. So those don't disappear, but we do lose the left and the right distinction. The other thing is renaming columns is very important, especially if you're dealing with joins and stuff, and that's pretty straightforward. You basically just use a rename on the columns. You in place true, which basically just means it will replace it within the place. And after renaming the columns, this is, for example, how we printed it out. The other thing you can do is reset your index. Resetting indexes is very common when you're dealing with data that needs to be time-stamped as well, because sometimes it doesn't really come in with an index. Sometimes the data, especially off of like IoT devices, tends to just come in like a stream, I guess you could call it. And so sometimes you need to reset the index. And if we add the drop, the column will also not be included. So let's go into some of the data science examples. So first thing would be autocorrelation. So autocorrelation basically refers to a degree of similarity between given time series and a lagged version of itself over successive time intervals. In other words, it's intended to measure the relationship between a variable's present value and any past values that you may have had access to. So we've already basically kind of seen this before when we saw the ADDK graph that was showing us some of the anomaly it was detecting within the machine vibrations. So in this example, we're actually using data from the National Oceanic and Atmospheric Administration Center for Operational Oceanic Products and Services. I really like saying that really, really long name, but everyone just calls it NOAA. Specifically here, we're looking at water levels and water temperature of a river in Santa Monica. And from there, we're going to be using the InfluxDB Python client library. A Jupyter notebook is also going to be linked at the end of this, so you can go check out the code yourself. But basically, this is completely free to access. The only thing to note is normally the data is not like real time. It's normally a little bit older, which is fine. So basically here, we connect up to the InfluxDB host, and then we go ahead and start querying it. So with that, we're selecting a mean degrees as H2O temp from the database, which has all the data from NOAA. And then we're basically plotting out those points in a data frame. We're getting the top 20 points, basically. And we want to go ahead and get a range of the range is going to be the timestamp, and then the plot is going to be a X and Y, basically. One of them is going to be time, one of them is going to be temp. The big thing here is just this query, which is grouping everything by the time of 12 hours and limiting to 60 values. So this is basically how this plot ends up looking. It's not obviously apparent whether or not the data will have currently any autocorrelation. For example, I can't detect so far the presence of seasonality, which would yield normally a pretty high autocorrelation. So we can go ahead and run it through the autocore, which is one of the pandas. This method computes the Pearson correlation between the series and its shift itself, and it comes automatically within pandas. That's what I was trying to get at. When the values are very close to 0, it normally indicates that there is little to no correlation within this data set. And as you can see here in ours, it is pretty close to 0. It's got, in fact, 0.0. It tends to be that there is a coefficient that has a value between -1 and 1, where 0 is no linear correlation, greater than 0 would be a positive correlation, and negative, obviously below 0, would be a negative correlation. So pretty straightforward overall. And then we can also go ahead and throw this on the autocorrelation plot. So we go ahead and plot the values that we just got. And we can see that the values for the ACF are within 95% confidence interval, represented by this basically solid gray line for lags greater than 0, which verifies that our data doesn't really have any autocorrelation, as we can see. The ACF can also be used to uncover and verify seasonality in time series data. So we'll take a look at water levels from the same data set, but this time we're going to be querying it, and we're going to be asking for a bit of a basically bigger time period. We want to see if the water levels change over the seasons, which sometimes, obviously, they probably would. Like, for example, in the mountains, a river probably would have less water flowing through it in the winter, and in the summer, when the snow begins to melt, you tend to have a higher water level. That would be seasonality in the most straightforward way. But we're going to check out a river in Santa Monica instead. And basically, the rest of this is pretty much all the same. The only thing that changed was the query. So just by plotting this data, it's fairly obvious that seasonality probably exists. It's evident by this predictable pattern in the data, but we're still going to verify it by plotting it with the ACF. So when we plot it, we can see that our seasonality period also consists of roughly what we would call 246 time steps. While it was easily apparent from plotting it in Figure 3, this isn't always the case. It's not always this straightforward. To be honest, it's because we were using a data set of water levels. It's not always this obvious when the seasonality would be, or when they would have seasonality. I'm going to link this article at the end of in the resources, but basically it goes over seasonal ARIMA with Python, and he shows that you must add a seasonal component to his ARIMA method in order to account for seasonality in his data set. And it's a great example of how using the ACF can help uncover hidden trends within the data. In fact, there we go. In fact, here are some of those resources. So you have the autocorrelation blog, which goes over a few different examples of autocorrelation. This Jupyter notebook goes over more examples and takes advantage of a few different autocorrelation examples, basically. Same ones pretty much in the blog. They link together. How to not use time series for forecasting pitfalls, and seasonal ARIMA with Python. I'm going to leave this up for just one sec. So, anomaly detection and forecasting. So, as I mentioned before, we're not going to go into forecasting today, but all forecasting examples can be found from this QR code, and they're all leveraging outside libraries, things like Facebook Profit, LSTM with Keras, and stats model Holtz method. For anomaly detection, though, we also have examples, which I'm going to link later, which go over things like autoregression, level shift AD, seasonal AD, and for multiple time series, which we're not going to be dealing with today. So, as I mentioned before, we're going to take advantage of the autoregression anomaly detection algorithm, which basically detects anomalous changes of autoregressive behaviors in time series. It can capture changes, which is basically a relationship between a data point and data points in its near past, and can be used for cyclic, but not really seasonal series in some situations. So basically, it's pretty straightforward. It's comparing the data that we have right now and the data that we have in, ideally, the near past, which what near is slightly different depending on your definition of near and the data that you're dealing with. So after we've acquired some data into a Pandas format, and this one's pretty straightforward, we're just using a CSV where we basically have a timestamp, a value, and a label of 0, which is pretty much not needed, which is also why we drop it. So we go ahead and drop the label, we put the in place true because we wanted to get rid of it, we go ahead and do a pandas to date time timestamp. So originally the timestamp looks like this, which is called Unix, which is obviously not human readable. It means nothing to us. So we go ahead and make it date time readable, so we can actually read this timestamp, see that this is a fake data set from 2016, and we set the index to that timestamp. So now we've just got a timestamp and we've got some values. So this is a visualization of this before the algorithm. So it's pretty straightforward. We've got a bunch of values. They're going over time. And yeah, very exciting. So we go ahead and apply the autoregression AD, which is pretty easy to import. You just use the addtk.data. And from there, we just go ahead and run this. So we're saying for every 10 steps, step size 20, go ahead and see if you detect any autoregression anomalies. And the rest of this is, for the most part, just defining, for example, the anomaly color red, the marker. Those are just kind of what we saw before in the last plot and that we're about to see in the next one. So this is pretty similar to what we saw before, but I will say with this data set, it was definitely a little less, like with the vibrations, we can kind of see with our own eyes. We could see some of those anomalies. But with this one, it's not quite as obvious, outside of, obviously, like super high spikes up, super high spikes down. That's kind of the only thing that's, visibly obvious to us at a human level. But you can see it's detecting anomalies a few a few different areas, obviously in particular this one and this one right here. But other than that, you just see a few random red dots, basically. And that is, for the most part, how you operate with this anomaly detection kit. And that's for pretty much all of the examples. It doesn't just have to be the auto-regression one. So these are a few of the resources. So basically, some of these are repeats as well. Yes, pretty much almost all of them are. So you've got your autocorrelation blog, the autocorrelation notebook. You have the forecasting and anomaly detection examples, all within Jupyter Notebooks. The two on the right-hand side are two articles going over like time series forecasting and the seasonal ARIMA that I mentioned. And in the bottom center, you also have the Apache Arrow docs, which obviously go over more examples on how to take advantage of Apache Arrows and just in general how to integrate it within your workspace, assuming that you're using some of the tools that I've already mentioned. I do suppose it would be kind of difficult to use none of the tools I mentioned and still you take advantage of it. The other thing you can do, so this link on the right, this Influx community, that's actually where you're going to find a lot of those QR codes go to, because that's where we put all of our projects, where we show off things like data analysis, but also more like fun stuff like monitoring plants, robotics demos. Basically, any demo lives on the right-hand side in our community that we take care of. And then on the left-hand side is just if you wanted to try out Influx or learn more about like how we built the engine with all these awesome open source Apache tooling and how other people are doing similar. And that is the end of my presentation. There's still definitely some time for Q&A, which I'm actually going to go back to. I like to leave it on this so people can take photos of it.
So I guess it would just like work with like Kafka or some sort of or like event hub kind of stuff.
Yeah, so the question was if this works with time series streaming data. And yeah, so for example, you can use Kafka with something like Telegraph. I don't know that Apache Arrows integrates directly with Kafka, but yes, you could use Kafka to stream your data into one of the tools above and basically take advantage of all this.
This data platform, it feels like influence data platform.
So yes, there's definite overlap with us versus something like Databricks or even, for example, Snowflake, which we actually have an integration with Snowflake via Apache Iceberg for that reason. What a lot of people tend to do is they tend to do real-time data monitoring on something like Influx with Grafana, or for example, with Grafana's own databases that they offer as well for observability. And then they'll store the more historical downsample data in something like Snowflake, so then they can take advantage of Snowflake's or Databricks, I'm trying to think of the word here, basically joining. Like you can join all your data within your data lake or your data warehouse, and it can be good for running different types of analytical workloads. I'm going to say right now, I don't think Snowflake is used quite as much for certain data science workloads, but it is used for workloads that, people, I'm trying to think of other words here, like in sales or something might use. Yeah.
Little bit like actual work for like just handling time series data rather than you have to build your own or improve your own library in Databricks, I guess.
Yeah, that is definitely true. So for example, Influx is without a doubt a specialized tool, a specialized database. So obviously, for example, we can't store really what would be considered more normal SQL data. And even some data that has timestamps on it, we wouldn't consider to be like an ideal match to be stored in us, to be clear. For example, when people log into a website, probably isn't really the data set that you're querying as much on those timestamps, versus in like an IoT environment, especially when you're dealing with lots of IoT devices, like I said, something like in a factory, that's when you use something like Influx, at least at the first start, like I said, for that real-time monitoring, for some of those original analytic workloads, but then yeah, you'll move your data into your data warehouse at some point, possibly.
Yeah, that makes sense. Do you guys support any like workflow orchestration?
I define workflow orchestration.
So let's say you have like a notebook and define a task, right? You want to run maybe 5 times with some variables. You want to run a different instance. And then you want some orchestration saying, hey, I want to kick off like 5 instances at this time, and later I'm going to kick off another 15. So instead of writing the thing like 15, 20 times, like can you just have this, basically, you have like a workflow, you can point into your notebook with some different variable and just, schedule it, or, basically a scaling up solution.
So it sounds like what you're describing is what we used to offer, which was like a task engine, which allowed you to run tasks on the database.
Yeah, or chain them together.
Yeah, exactly, or chain them together. Currently in the new version, we don't offer that, but we're planning to. We're working on integrating some other tools to allow that orchestration to happen, but right now it would happen outside of the database.
Okay. So it sounds like actually if we're collecting some, user events with some really rich data, we're talking about maybe 2, 3 levels of like JSON nested, it's probably not going to be a good fit for this because you guys are expecting something from like IoT devices with like really straightforward, very rigid like schema, right? And then it just really fast processes.
Exactly, yeah, that's definitely true. For example, some people, what they'll do with what you just described, like a rich data set, because sometimes they are dealing with that, what they'll do is they'll actually divide their data. They'll send a lot of like the metadata, the richer data, onto a more appropriate database, and then they'll have a very bare bones timestamp, like 1 or 2 value data set within Influx. I've definitely seen people do that, especially because some data is already rich off the bat, like just in general within the IoT world. Normally sensors are pretty bare bones, I would say. Like the values they send in are very bare bones. It's normally only just 1. But occasionally you do end up with, those richer data sets, and this cannot always be the perfect place to like store that super rich data set, if that makes sense. Like for example, we max out at like 200 rows, and most time series databases, including our old version, would max out more at like 50 rows or 50 column headers. So you couldn't have a super rich data set. But again, if you think about things like IoT or observability data, you don't tend to have that outside of traces, which I would say is definitely a rich data set.
Yeah. What type of like data lineage support this platform provides?
What would that be exactly?
Data lineage. So basically, I think the trace that basically you were talking about, saying, hey, this table is coming from, what other table, and basically down the chain how a data flows through a pipeline or.
So we normally deal with just, I'm going to just call it like a stream in data. So for example, we don't allow you to do things like outside of like downsampling and aggregation. We don't normally see people like go back in and re-edit data, for example, is just streamed in. So like you don't go back and be like, actually, no, the pressure wasn't 20, it was 19 at this minute. It's not really like that. It's just constantly streaming in. So that's how we tend to handle that. And that's, when I'm mentioning these questions, I'm also answering them more broadly. In general, this is how most time series or NoSQL DBs handle this kind of data set.
That's true. That's structured streaming.
Yeah, that's basically just how it goes.
The history. Awesome. Thank you so much.
We're good. Thank you, guys.